Hello, hello, guys and gals. Welcome back. In this video, we're going to be talking about 5.1c, which is going to be talking about all of the things that we can do or all of the things that affect our reaction rate, okay? Now, there are 5 main things that affect our reaction rate, and most of them we can change. Most of them we can change, and most of them have to do with collision theory. We're going to be affecting one of those 3 requirements of collision theory, okay? So, the 5 things that control the rate of reaction: the nature of the reactants, the concentration of the reactants, the temperature, surface area, and catalysts or inhibitors. So let's get going. Now, the nature of the reactants recurs to a couple of things. First and foremost, it recurs to the phase that the reactants are in, because solids tend to react much more slowly than liquids or gases. And let's take a look at why. Solids, the particles are stuck in set configurations. They don't move over each other. In fact, they don't move over anything. They stay where they are for the most part. So your chance of collision is very low when you're reacting to solids. That's not to say that it doesn't happen. It's just to say that if it happens, it's going to be a lot slower than a liquid or a gas. Because collisions, remember that's the first requirement of a reaction from collision theory, particles must collide. The more collisions that you have, the faster your reaction is going to occur, right? So if your solids cannot collide, they're not really going to react very quickly, versus your liquids and your gases that are spread out, that can move over each other, they're going to have that option to collide a lot more often, okay? Now, that is something that we can control to an extent. Not everything can dissolve, and so you can't turn everything into an aqueous solution to make it move better. And some things burn instead of melt, and so not everything is going to be able to get turned into a liquid or a gas. So just know that when you can change the phase of a reaction, solids are going to react slower than liquids or gases. Another piece of a nature of reactants literally just comes down to the chemical properties of your reactants. Is your reactant made up of ions? Because ions tend to react very quickly, oppositely charged ions, right? Do your reactants have lots of bonds? Because the more bonds you have, the more bonds you have to break. The more bonds you have to break, the more energy that you need, and the more energy you need, the slower your reaction is going to go. Are your bonds super strong in your reactants? Remember that double and triple bonds are way stronger than single bonds. And so if you've got something like nitrogen gas, which is 2 nitrogens triple bonded to each other, it's going to be pretty difficult to break that bond. And that's not really something you can control. If you have to work with nitrogen gas, you just have to work with nitrogen gas. And you're going to have to find a way to overcome that triple bond. The good news is that there are things that allow us to overcome those bonds that we can control, okay? Like the phase and like the concentration, okay? So the concentration, keep in mind that the concentration of a solution is moles per liter. So let's say we have 1 liter here, and let's say that our concentration is very low. Let's say we only have 2 atoms in this whole liter of water. That means that you can have 1 collision. It means your reaction is going to be pretty slow, right? Versus if you have several particles in this and you have a very high concentration, well, then they don't really have any choice but to collide, right? Think about it this way. Compare walking through the lobby during class to walking through the lobby during break. Because I walk through the lobby during break and it is insane. You can't move 3 feet without bumping into somebody. And that's kind of like what we're doing with concentration. When we increase the concentration of a substance, we're increasing the number of particles that that substance has. If we increase the number of particles that it has, we're going to increase the number of collisions. And the more collisions that we get, the faster our reaction occurs. Okay? So that's how concentration affects our rates and how it's related to collision theory. The third thing that's going to affect our reaction rate is temperature. Heat 'em up, speed 'em up. It's my favorite thing my kids last year like to say. Heat 'em up, speed 'em up. When you increase your temperature, you give your molecules more energy. That means they're going to move faster. If they're moving faster, they're going to collide more often, okay? Think about it like if you've got 2 3-year-olds in a room and they're just walking, they're not very likely to run into each other. But if they're running around hyped up on sugar, they're going to slam head first right into each other, right? So the more energy, or the faster that the molecules move, the more likely they are to collide, and more collisions leads to a faster reaction. But here's the thing, temperature actually affects two pieces of collision theory, and you've got to know that. AP is very picky about their free response questions, and if they ask you a free response question about why temperature affects the rate, and you don't mention both prongs of this, they will not take your answer, okay? So, heating up the molecules speeds them up, it makes them collide more collisions increases your reaction rate. But it also increases the energy of the molecules themselves. And so when they collide, there's more energy behind that collision. Recall that the third requirement is that molecules have to collide at the right energy, called the activation energy. So if your molecules have more energy, they're more likely to collide with that energy that they have, that extra energy, and they're more likely to meet your activation energy. Okay, so increasing your temperature is going to increase your number of collisions and increase the energy at which they collide. Obviously, decreasing your temperature would do the opposite, right? The next thing we're going to talk about is surface area. So with the exception of gaseous substances, reactions occur at boundaries. So if you drop acid on your finger, the boundary is your finger. Your bone inside your finger is not going to hurt because it's not exposed. You can't react with something that's not exposed, right? So the more pieces that you have exposed, the more collisions you're going to have, and the faster your reaction is going to go. I like to use my calculator for that because it's just a really quick, fast, easy way to talk about it. If my calculator were a molecule, there are 4 places that it could collide with something. It could collide with something here, 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 right? 6 if you want to include the sides, but they're kind of tiny. So here and here. So there's 6 places that my calculator could collide with something. But what if I take this off of it? Now there's 6 places that this piece could collide with something, and there's also 6 places that this piece could collide with something. Now that's 12 more places for possible collisions, or 6 more places, but a total of 12 places for possible collisions. So increasing your surface area increases your chance of collision, and the more collisions you have, the faster the reaction goes. Now in real life, what we tend to do is we tend to take solids and we grind them up into powder. Coal dust is way more explosive than coal itself. Coal is just flammable. Coal dust, you'll blow up a whole mine, okay? So the more surface area, the more collisions, the faster the reaction. The last thing that really affects your rate, that's like a common thing, are catalysts and inhibitors. Now we know what catalysts are. We know that they increase the rate of the reaction. The question becomes why. The fact is, a catalyst comes in and basically offers a shortcut for the reaction to occur. We know that complex reactions occur in steps, right? Well, a catalyst comes in and they're like, you're doing it in 5 steps? Dude, I could let you do it in 3. Let's go. And so, not exactly that way. They might both be in 3 steps. What's really happening is that the shortcut that the catalyst allows the reaction to go through has a lower activation energy. It does not take as much energy to go through the catalyst as it does to go through the regular reaction. So a catalyst does not lower the activation energy of the reaction. Okay, if you take a shortcut, the original path is still there. What a catalyst does is it offers a new pathway with a lower activation energy. By lowering the activation energy, you make it more likely that your collisions are going to hit with that energy and that they're actually going to be fruitful, right? So if you add a catalyst, you can add a homogeneous catalyst, which is the same phase as your reactants, or a heterogeneous catalyst. Most of the time we like to do heterogeneous because it's easier to separate if your catalyst is solid but your products are liquids. And also they don't degrade as quickly. Enzymes. Enzymes are great real-world catalysts, okay? And I'm sure you talked about enzymes all the time in biology. AP loves to talk about enzymes because they are real-world catalysts. They're offering a shortcut with a lower activation energy. Obviously, inhibitors do the opposite. Now, there are other environmental factors that affect the rate of reaction. Pressure, volume, those are the 2 biggest ones, and some others. But every time you get asked this question, just think about how is it going to affect my number of collisions, my orientation, or the energy at which my collisions occur, and you'll be able to answer the question, okay? Let me know if you have any questions.